Alright, this is Professor Denholtz, and I'm going to be demonstrating Chapter 5, Problem 57. And so this problem, you should have it in your textbook. Basically, there's a pail that you're swinging vertically, and you're swinging it with a radius of 0.6 meters. And we want to know what the minimum speed is, given the pail is at the highest point in its motion without spilling the water. And so let's just kind of visualize this problem a little bit. So there's, a person who's kind of swinging a pail in the vertical direction, and the length that they're swinging it, of their arm. That length is the radius here, and so the length is going to be equal to 0.6 meters. Now we can draw this a little bit more clearly, and so there'd be a pail swinging, and there's some kind of a connection to the pail. And the pail is full of water. And so at the top trajectory, we're going to be in a position where the pail is upside down, and there's water in the pail. Obviously, gravity would want to pull the water downwards, and there's nothing that's going to be holding it in place. Now, additionally, because there is the water, and it's up against the surface of the pail, well, there's physical contact between two different objects. And so when we have that, we get a normal force, and that normal force has an action-reaction pair from Newton's third law. And so in this case, when we're at the top of the trajectory, if we view the water as a particle here, it's going to have the force of its weight on it, and it's also going to have the normal force, which is the action-reaction pair from the top of the pail. And so here the pail is above the water, so it can only push the water down. It can't pull the water up. And so the normal force is going to be pointing downwards. Now, a few other things that we know about a situation like this is that we have that we're accelerating in the downwards direction because that's the center of the circle. We're always accelerating towards the center of the circle, and so I'm going to treat this as being positive, and it's also the direction of A. And so now we've kind of set up our problem. We know where A is pointed, we know the forces involved, but there's one other component. So here we don't just want to find the velocity, we want to find the minimum velocity that we need to do this. So what would happen at the minimum velocity? Well, the minimum velocity for the water to stay in the pail when it's upside down would mean that the water is just beginning to fall from the pail, and there's no longer contact between the water and the surface of the pail. And so if we have our pail over here, and the water is just losing contact with the pail, well, then there's no more normal force, because normal force is a contact force. So for this minimum velocity, we would say that there is no normal force. And so we know that there's acceleration because the water, the trajectory is a curved trajectory, so there's some kind of turning involved. And so that means we have to use Newton's second law, which states that the net force is equal to ma. And in this case, I'm going to go a step further and specify that's the net force in the y direction is equal to may. I'm also going to note that from our free body diagram, the sum of the forces is just equal to W. There's only one force in this situation on the water, and that's the force of its own weight because it's not touching the pail anymore. So the sum of the forces in the y direction is going to be equal to W, which is the same thing as mg. So if we set these two equations equal to each other, we have MAY is equal to mg. We know we could cross off the m's. And we also know that this is circular motion. And so if you recall, we had an equation for circular motion that A is equal to v squared divided by r. And so now I'm going to substitute in this for this, and we get g is equal to v squared over r. Well, this we know, this they gave us, and this one is what we're looking for. So we're going to isolate v, and if we do that, we get v is equal to the square root of g times r, and then we just plug in the values. We know that g is 9.8 meters per second squared, and r is 0.6 meters. And so we get a value of the square root of 9.8 times 0.6. And that would be our answer for the minimum velocity. And so that should be a little bit less than 6. So I don't have a calculator in front of me, but that's how you come to the answer.